Hello everyone, you are welcome back to this tutorial on digital modulation. Today's tutorial we are going to focus on amplitude shift key or binary, so we can call it in short BASK, binary amplitude shift key. Yes, so this is what we are going to talk about today. So basically this amplitude shift key is a type of digital amplitude modulation which actually represents the binary data in the form of variation in the amplitude of a signal. So what I mean is that it actually represents how the carrier signal changes with respect to the change in the basic signal, which is our digital data. So any modulated signal has a higher frequency or higher carrier frequency, as I said earlier on. The binary signal, when ASK modulated, give a 0 value for low and then a high value for, let's say, a 1 value for high. For any modulated signal, right, since it's a 0 and 1, the 1 aspect gives high and then the 0 aspect gives low. That's for the amplitude. So if you look at this particular diagram over here, you can see that this is our binary data, and this binary data, it's being transmitted via a carrier frequency, and this is our carrier. So based on this carrier, right, based on this carrier, it's going to transmit it in such a way that whenever it is 1, it will transmit the carrier, right? That means that the message is being transmitted. Whenever there is 0, it will attenuate everything from there. So as you can see, everything has been attenuated from here because this part of the data is 0, or the binary data is 0. So when we see that here, the part of the binary data here is 1, 1, you can see that it is transmitting. And then because here it's 0, it attenuates everything. That's how the binary ASK works over here. So this is a graphical representation of the binary ASK. So to know more about how we are going to obtain an ASK, which is the amplitude shift key modulated wave, we would like to learn more about the working of the amplitude shift key modulators. And let's quickly run into the amplitude shift key modulators, which is, let's say, binary ASK modulators. So as I will say over here, for the ASK modulators, it has a carrier signal generator and also a binary sequence from the message signal and then the band limited filter as well. So before I proceed with the binary ASK modulators, let's quickly look into the block diagram of how binary ASK looks like. So basically, if you want to modulate, do an amplitude shift keying over here, you will need a digital data, which is of course the zeros and the ones. That is your information. And here we use a modulator called unipolar modulator, which is unipolar NRZ. This NRZ means that it's non-return to 0. Basically, you have other modulator which is return to 0. So let's quickly talk a little bit about this non-return to 0 unipolar, right? So for the non-return 0 unipolar non-return to 0, it uses only one voltage level. That is usually at the positive side, right? So if we have the number line here, this is the positive side and this is the negative side. So basically it uses only one voltage level, which is usually the positive side, and it's used to represent both zeros and ones. So it's like this, something like this here. So 1, 0, 1, and so on. Even though the unipolar return to 0 also uses only one voltage level, which is also usually positive side, but the original, let's say, but the signal return to 0 after each bit, regardless of whether it is 0 or 1. But when we come to the unipolar non-return to 0, the signal does not return to 0 between the number of bits, right? So it actually remains at a constant positive voltage for a 1 bit and at 0 volt for a 0 bit, right? So coming back to the unipolar return to 0, because the signal returns to 0 after each bit, regardless of whether it is 0 or 1, it means that there is a transition in every bit duration, which makes it self-clocking. That is, there's no separate clock signal needed for it, right? And it requires twice the bandwidth of the non-return to zero for the same data rate, data transmission or data rate. So that's a little bit about the unipolar non-return to zero modulator and that of unipolar return to zero modulator. So let's quickly go back into whatever we are doing so far. So getting into the block diagram of how the binary ASK is generated, as I said, you need a digital data or your information, and we are going to represent the digital data as dt, right? And as I said, we need a modulator, and the modulator that we are using here is a unipolar non-return to zero modulator. And so for that matter, this is my dt, feeding my dt into the modulator over here, which is unipolar non-return to zero. Now I now have my bits over here, right? I now have my bits over here. So looking at this part, what do you think the unipolar non-return to zero did over here? As I said earlier on, you are receiving the data in the discrete domain, and this unipolar non-return to zero will modulate it in such a way that we get the zeros and ones as our information. And when we get the zeros and ones as our information, we feed that zero and ones in a balanced modulator. So basically, the work of the unipolar non-return to zero here is to modulate the digital signal into a binary form, which is the zero and ones, right? Let's say the discrete, let me say it that way, the discrete signal or the discrete data into the digital form, which is the zeros and ones, and that one we are going to represent it by B of t. So when we represent it by B of t, we pass that information into a balanced modulator. A balanced modulator. And we use a carrier AC cos omega ct, which is our C of t, to modulate it. And the output is going to give us BASK signal. So based on this, since it's a balanced modulator, as I said in analog modulation, sometimes you have to pick it as a product modulator, and therefore we can say that our output S of t here, let's say S of t here, it's equal to the binary data B of t AC cos omega ct. So this will be finally our modulated signal for binary ASK. So this is actually the block diagram for the binary modulated signal that we have. So let's do a little bit of analysis here. So for the generation of binary ASK, if the binary is 1, right, it means that B of t, which is the binary data, it's 1. Therefore, S of t is equal to 1 multiplied by AC cos omega ct. And therefore, you can see that the carrier will be transmitted. That's why you were seeing this one over here. This one over here. Because here, the binary B of t was 1, and therefore, it was transmitting. So looking at the other side, where the binary B of t is equal to 0, the x0 of t also gives us 0, because we will have 0 times the carrier, which is AC cos omega ct. And for that matter, we are going to get 0. That's why you saw that this place was attenuated whenever the binary data was what? 0. So basically, we can say that our S of t in the general form for binary ASK, it's equal to B of t AC cos omega ct. And therefore, we are assuming that if B of t is equal to 1 volt, then the bits value here is what? 1. But if B of t in terms of the voltage aspect is 0 volts, it means that our bits is equal to what? 0. That's something that we need to take note of. And B of t, which is the binary data, is a unipolar non-return to 0 signal. So looking at the block diagram for the detection of BASK, basically what we do is that as we did in analog modulation, we pass the modulated signal through a modulator. And because we are doing a synchronous demodulation or detection, we use the same carrier wave to detect it. And this is almost similar to that of analog modulation, demodulation. And this is because this is the block diagram. So we assume that our S of t that we got here, it's equal to B of t AC cos omega ct. Therefore, if I'm passing S of t, which is the modulated signal, through a balanced modulator, and then I detect it with the same carrier wave, which is AC cos omega ct, the resulting aspect that I'm going to get is x of t. And this x of t is the output of my demodulator, right? This is the output of my demodulator. I passed the modulator signal inside and with the carrier signal as well, and I got an output. But because of the nonlinear nature of the modulators, we are going to get some bit of harmonics inside, right? And therefore, we need a filter. So in digital modulation or demodulation, we are not going to use, as in analog modeling, which is having a filter of low pass filter, high pass filter, and then band pass filter. For digital modulation, our filter is being represented by an integral, right? It's being represented by an integral of from 0 to TB of the signal multiplied by dt. So basically, this TB here is the bit rate. The TB here is actually a bit rate, and we'll talk more about it in the subsequent videos that we are going to do. So basically, that's the TB here is a bit rate. So when this is actually our filter, instead of saying low pass filter, we pass it through this filter, and when we pass it through this filter, the resulting answer is going to be passed through a comparator. So the comparator is the one which is going to, let's say, threshold voltage comparator, right? So this comparator is the one which is going to show us whether the signal which has been demodulated is either a binary 1 or binary 0, right? So what we are going to do here is that this is our threshold, and then the output, let's say, the output of the threshold, if, let's say, let me say here's y of TB, right? So if this y of TB is greater or equal to the V threshold, right? The V threshold, it means that the data which is coming in is what, or which has been demodulated, is binary 1. And if y of TB is less than V threshold, it means that, or less than V threshold, it means that the data which is coming in is equal to binary 0, right? That's what you need to take note of. That's what you need to actually take note of. And we are going to talk about it one after the other, and then I'll show you what you are going to use here as your threshold for the comparator. All right, sure. So this is a little bit about how the binary ASK work, and we are going to do a deep mathematical analysis in my next tutorial. So thank you for watching, and see you in my next video.